Hello everyone, I'm Hyuk Lee and the speaker of Feasibility of Networking Technology for Smart Farm, LoRa versus APRS. As everyone knows, our topic is the Internet of Things. There are 7 more students and Professor Smith. My presentation consisted of 6 parts. First of all, our use case is as follows. There is a farmer who lives far away from his farm. He wants to get data like temperature, soil humidity, and more from his farm. Our goal, our goal was to figure out a way for him to get the data. We thought we could solve this problem with the IoT-based smart farm and decided to find a way with the scalability, long range, low cost, and energy efficiency in mind. Although LoRa is used a lot in IoT these days, few studies compare it with the other communication methods. As I mentioned earlier, LoRa is mainly used in IoT world already, but we thought that by using APRS, the data could be transmitted farther. Since APRS and LoRa are similar, we decided to compare the two to see which one performed better and more reliably for our use case. LoRa is short for long range and is a low power network which sends data wirelessly. The frequency in North America is 915 MHz, and it is now widely used in IoT. APRS is short for Automatic Packet Reporting System and is a network based on radio. It is used in long distance communication. Its frequency is 144.39 MHz. The environment was established for LoRa's communication distance test. But LoRa's communication distance was so short at 100 that we modified LoRa's transmitter and receiver code. TX power was changed to 13, signal bandwidth to 125E3, and coding rate to 5. After these changes, we confirmed that the communication distance increased to 1 kilometer. The APRS initially had only a communication distance of 50 meters. This is because we did not understand the characteristics of the antenna, the ground condition, the height, and the parallel state of the two antennas well. The antennas we used were magnetized, so we had to put them on the metal surface to increase performance and raise them high to receive less interference between the antennas. In addition, the direction of both antennas should be parallel so that they are propagated well. Considering these factors, antennas were installed and the communication distance was increased to 890 meters. In fact, it could have been more possible than this, but it was physically impossible to get further away from the test environment. However, due to the topographical factors of the test environment, the height difference between the two antennas widened by about 10 meters, resulting in longer distance than when the heights were the same. The antennas we used had different antenna gains, so we adjusted the transmission power of each transmitter to equalize the EIRP of LoRa and EIRP of APRS. EIRP stands for Equivalent Isotropic Radiated Power and is obtained by subtracting the cable loss from the output power of the transmitter and adding antenna gain. The transmitted power was measured through the spec analyzer, and since the measured transmission power was the final output power sent to the antenna, we could say that this value was the output power of the transmitter minus the cable loss. Here, PT is output power of the transmitter, and LC is cable loss, and GA is antenna gain. After figuring out both APRS and LoRa devices, we tested them at Purdue Agronomy Center for Research and Education. We installed the receiver antenna on a long pole for both APRS and LoRa. But LoRa's receiver antenna was limited in height because we installed it next to the APRS antenna installed on the farm. So LoRa's receiver antenna was installed at 4 meters and APRS receiver antennas at 6.4 meters. The APRS transmitter antenna is placed on top of the car with a team member in the car holding LoRa's transmitter antenna at the same height. We then drove along continuously checking to see if each signal had reached. Every time communication was made, we marked its location on Google Maps, and APRS did not generate signals when testing LoRa to minimize radio interference, and vice versa when testing APRS. Also, to prevent radio jamming by cell phones, we did not use the cell phone during the test. And we stopped the car for 30 seconds and tested it to see if it received the signal because the signal could be lost while moving the car. When the signal was transmitted, we moved further, and if it wasn't, we went back. In this way, we checked that the farthest distance that the signal was transmitted. We conducted it at a total of 3 tests. And as mentioned earlier, we did not understand antennas well at first, nor we didn't know the concept of EIRP. So we used a transmitter and antennas with the spec of the table in front of you in the first table. In the first test, LoRa had a communication distance of 160 meters, and APRS had a communication distance of 1.3 kilometers. In the case of APRS, it would have been longer because we mistook other signals for APRS signals, and actually much shorter than this one. During the second test, we found a broken antenna, replaced it with a new one, and increased the transmitted power of the APRS. The second test showed that LoRa was 4.2 kilometers and APRS was 0.70 kilometers. The final test was carried out with the same EIRP of LoRa and EIRP of APRS, while LoRa was delivered up to 4.2 kilometers as before, and APRS up to 860 meters. This is our final setup. For our testing, we used Arduino and antennas for both technologies. Many LoRa deployments consist of devices like this. We use the LoRa shield to send signals. Many APRS devices also utilize Arduino and antennas. But we could not find an APRS shield, so we made a simple circuit using a HX1 transmitter to send signals. On the left are LoRa's transmitter and receiver, with only 2 antennas different and the rest all identical. On the right are the APRS transmitters and receivers, which use an Arduino and a HX1 chip as the transmitter, and the receiver used the USB B200. We need to know the theoretical distance for LoRa and APRS. We could use Fritz's transmission equation to get it. PRX is the power of receiver, PTX is the power of transmitter, and GTX is the gain of transmitter antenna. GRX is the gain of receiver antenna. F0 is frequency of wave. C is the speed of light, and the R is the distance between transmitter antenna and receiver antenna. As we know everything except the distance, we could get transmission distance with this equation. And there's an important thing in our testing, funnel zone. The funnel zone is an elliptical space where radio waves can be transmitted well. It depends on the wavelength of the radio wave. There should be no obstacle in funnel zone for the radio waves to be delivered perfectly. Assuming that the radio waves belong to funnel zone, We get the theoretical distance of LoRa and APRS respectively by phase transmission equation. It can be transmitted up to 9.3 kilometers using LoRa, and it can be transmitted up to 59.7 kilometers using APRS. But there is a big difference in the height needed. The height needed for LoRa is 27.79 meters, but that for APRS is over 176.02 meters. It was much higher when it compared to LoRa. When we tested at the party farm, the height of antennas was only around 2.35 meters and 4 or 6.4 meters. So the tested distance of LoRa was 4.2 kilometers and APRS was only 0.86 kilometers. When we got the efficiency constrained by height, LoRa was 45.16% and APRS was 1.44%. We had been able to find out from this that APRS affected more by flange zone than LoRa at this height. So our conclusion is that LoRa is more appropriate than APRS in Egg IoT, since at least 60% of the flange zone radius is required to communicate. The antennas must be installed at a height of not less than 105.61 meters to send data using APRS to maximum distance. Installing antennas so high will cost more than the advantage of being able to transmit data far away. Therefore, LoRa is more suitable for Egg IoT than APRS. This is our limitation. The first is that we use the antennas which have different antenna gains and the transmitters which have different transmitted powers. The second is that there was no crop canopy when tested on the farm. If we had tested it when there was a canopy of crops, the results would have been different. The poultry farm we tested it had a lot of corn, but the corn was quite high, so there was a great possibility of jamming the radio waves if there's a lot of corn. There was corn in the first test, but there was nothing in the final test because it was all grown. This is our future work. The first is using the same gain antennas for LoRa and APRS. We wanted to use antennas with the same antenna gain because we thought that we could make an accurate comparison only if everything other than the communication method was the same. The antennas we wanted were not delivered on time, so we could not use what we wanted. The second is to install antennas on a higher structure. The height of installed receiver antennas was too low. As I mentioned earlier, it took quite a high height to avoid the flange zone. On the other hand, considering the height used on the actual farm, we were fine at one height. But our initial purpose was to deliver data to to farmers who live far away. So we needed a high height. Therefore, more accurate results could be obtained by using the same gain and higher installation and the same transmitted power. This is the end of my presentation, and if anyone has any questions, please do so. And thank you for listening to my presentation. Thank you.